Just before noon on December 6, 2025, a low, violent roar threaded through the high glaciated valleys along the Alaska-Canada border. What exactly broke beneath those ice-scoured peaks? Did a long, locked slice of crust suddenly give way, or was the event a relay, one fault tripping another like falling dominoes? And might this tremor be a modern echo of the famous 19th-century Doublet that once rearranged Yakutat Bay? A magnitude 7.0 earthquake shook the Hubbard Glacier region, and while the human story of startled towns and rattled cupboards is vivid, the deeper and far more intricate story is written in stone-collided plates, tangled fault strands, microplates barging northward, and a history of twin quakes that teaches us how the crust remembers and responds. The first technical clue comes from depth and location. The rupture originated at a shallow depth of roughly 10 kilometers, approximately 6 miles beneath the surface, placing it squarely in the brittle upper crust where earthquakes make the loudest, most destructive noises. Shallow quakes concentrate their energy closer to the surface. Imagine snapping a twig, compared with snapping a thick branch several meters about 10 feet below a pile of leaves. The nearer the snap to the surface, the more of the energy you feel above ground. Because this shock was shallow, local stations recorded intense shaking for tens of seconds. Communities within a couple of hundred kilometers, about 125 miles, felt the ground sway. Instruments as far away as regional population centers logged the shaking signature, but there was no major tsunami generated, and coastal gauges did not register destructive surges. The lack of a widespread tsunami is a technical point worth dwelling on in broad terms: lateral or strike-slip motions, where blocks slide past one another, move water far less efficiently than vertical motions that uplift the seafloor. This quake's physics favours side-to-side motion more than vertical popping of the seafloor. Geologically speaking, southeast Alaska is not a sleepy stretch of stable crust. It is a knot of plate boundaries. Across geological time, the Pacific Plate has been inching northwestward relative to the North American Plate, and the motion does not take a single neat highway. Instead, that relative motion is partitioned among a network of faults. One prominent set of streets in this tectonic city is the transform family faults, where blocks slide horizontally past one another. The Queen Charlotte Transform offshore, which continues onshore as the Fairweather fault system, is the major conveyor of that horizontal motion in this part of the globe. Along this boundary, the motion is largely strike-slip. Visualize two rough hands rubbing past each other sideways. Fault strands trace northwest-southeast lines, and the newly ruptured segment near Hubbard Glacier sits at the interface between a main transform and a connector strand that threads into the continental interior. This connector is like a chain link that transmits motion from the nearly offshore transform system into onshore structures. When that link slips, it can relieve accumulated strain in a sudden, sharp event. Adding further complication is the Yakutat Microplate, a block of unusually thick and buoyant crust that has been travelling northward and colliding with southern Alaska for millions of years. Unlike a thin slice of oceanic crust that readily dives beneath a continent, the Yakutat chunk is stubborn, and its arrival has folded, faulted and thickened the edge of the continent. Think of it as a slow bulldozer scraping against the continental margin, creating a zone of complex deformation where stress is concentrated and transferred among multiple fault systems. That collision has seeded the region with many potential rupture surfaces, interleaved faults that can awaken with little provocation once stresses exceed their thresholds. Over the last century, scientists have documented how this collision can produce not only single large earthquakes, but also complex sequences and sometimes doublets where two major shocks occur in close succession. The term doublet deserves unpacking because it speaks to the nature of stress interaction in the crust. A doublet is essentially two comparable earthquakes that occur nearby in space and closely spaced in time. The 19th century example in the Yakutat Bay region is a canonical case. In early September of 1899, a very large quake ruptured along portions of the margin, and within days another similarly large slip followed. In that story, the first massive rupture altered the stress field so substantially that a neighbouring patch of fault was pushed past its breaking point. The physics are straightforward in principle. When a substantial portion of a fault releases stress, the pattern of forces in the surrounding crust shifts. Some patches see stress reduced, while others gain it. If an adjacent patch has been loaded close to failure, that added nudge can send it over the edge. In the late 19th century instance, the doublet behaviour was so dramatic that coastal landforms rose and fell by metres several to many feet, and tsunamis were triggered locally. Modern sequences, even when smaller, can still display the same choreography of stress transfer. Turning back to the recent Hubbard Glacier rupture, seismological analyses reveal a coherent narrative. The rupture orientation and early aftershock distribution match a northwest-southeast fault strand, consistent with the known geometry of the Fairweather Queen Charlotte system and its connector strands. The initial rupture propagated preferentially toward the northwest, and in the first minutes several aftershocks of notable strength followed, mapping out the fault size and orientation. These aftershocks are not mere side effects. They are the crust's way of rebalancing, revealing which parts of the fault slipped and which remained locked. Each aftershock is a data point. Its location, magnitude and timing help seismologists construct a three-dimensional picture of the rupture. As scientists accumulate those points, they effectively draw the fault's rupture surface in space. Mechanically, the slip appears to be predominantly horizontal strike slip, with a right lateral sense that reflects the regional plate motion. To give an analogy, viewers can imagine two columns of interlocked jagged bricks pushed slowly past each other. They resist because the teeth of the bricks interlock, storing elastic strain like a stretched spring. Eventually, the interlocking fails at one weak point, that patch slides, and the inertia of surrounding locked patches may cause them to slide too in a cascade. If the sliding patch is shallow and substantial, the shaking is pronounced at the surface. The crust's memory the accumulated strain, since the last large release on that patch controls how big the shake will be. In this case, decades of slow motion had built enough strain for a magnitude 7 class release. Why did the rupture occur where it did? The local structural setting offers some clues. The Fairweather system in southeast Alaska is patched with multiple strands and stepovers where the fault jumps laterally. Those stepovers are inherently vulnerable because they concentrate stress. Imagine two lanes of traffic that suddenly force vehicles to change lanes. Collisions are more likely at the switching zone. Similarly, where a transform system transfers motion into a more complex interior fault network, the stresses concentrate and make a sudden slip more probable. The Hubbard area is such a junction. It is where the offshore transform links with inland structures, and the Yakutat block's edge compounds the complexity. In such a mechanical environment, even relatively modest changes in stress from prior earthquakes, seasonal loading from snow and ice, or regional tectonic adjustments can tip a marginally stable patch into dynamic failure. The short list of immediate geological consequences begins with aftershocks, which typically persist for days to months following a large rupture. Initially, the aftershock rate is high. Many small to moderate events radiate from the main rupture as neighbouring patches adjust. These aftershocks not only reconfigure stress locally, but can also destabilize slopes. Southeast Alaska's steep topography and glacially carved valleys are notoriously susceptible to earthquake-triggered landslides, especially in places where heavy winter snow or saturated soils add weight to an already stressed slope. The region's history warns us that magnitude 7 events, and even smaller ones, when correctly located, have previously triggered massive landslides that produced local tsunamis in narrow bays. The infamous 1958 Lituya Bay megatsunami, for example, followed a large earthquake that triggered a colossal slope failure. The result was a wave that scoured vegetation from mountain slopes hundreds of meters more than 1,000 feet above sea level. While the Hubbard Glacier earthquake did not produce a similar catastrophic tsunami, its occurrence reminds geologists and emergency managers that the geological topography here elevates the landslide and local tsunami hazard. Another technical impact is permanent ground deformation. GPS stations, even those located tens to hundreds of kilometers, roughly 10 to 60 miles away, often record measurable offsets after a magnitude 7 earthquake. Those offsets may amount to centimeters or tens of centimeters, roughly fractions of an inch to several inches of permanent displacement. In human terms, these are small numbers, but they are the crustal fingerprints of a fault-slip permanent movement that will be encoded in the rock record. Field teams will likely carry out coastal and inland surveys to measure subtle uplift or subsidence along the shoreline and in river valleys. Comparing these measurements with historical records and with data from previous big events, including the 19th century Doublet, yields a clearer picture of how the crust deforms during large ruptures in this tectonic regime. The Hubbard Glacier event also offers scientists an opportunity to refine models of stress transfer and earthquake interaction in a complex microplate setting. Each large earthquake is an experiment run by nature. By measuring how the crust responds, researchers can improve numerical simulations that estimate how one rupture may alter the likelihood of another. For instance, if the recent slip increased shear stress on an adjacent segment of the Fairweather system, that segment could see an elevated chance of failure in the months to years ahead. Conversely, some segments may be stress-relieved and therefore less likely to break immediately. The mathematics of these interactions is well developed, but real-world data, precise locations, focal mechanisms, and geodetic offsets are required to constrain the models and make them useful for hazard assessment. Turning back to the broader historical context, the cluster of major 19th century events in Yakutat Bay illustrates how the crust in this region can behave in ways that are neither random nor singular. The doublet pattern from the late 1800s shows that a significant rupture and a nearby companion can both occur within a short span, reshaping coastlines and generating tsunamis. That historical precedent informs how seismologists interpret current sequences. When a major shock occurs, the immediate question is not simply how big was it, but how did it change the stress field, and which neighbouring faults now face a new loading. The answers do not yield precise forecasts. Earthquakes cannot be predicted like storms, but they allow probabilistic assessments that feed into preparedness measures. For the technically curious viewers, the focal mechanism solution, The Beachball representation that seismologists use to infer faulting style for this earthquake indicates a dominant strike-slip motion with a fault plane oriented roughly northwest-southeast. The nodal planes in the solution correspond to two possible fault planes, but combining the focal mechanism with the aftershock distribution and geological mapping resolves which plane is more likely to have ruptured. In this case, the plane consistent with the regional transformed geometry best matches the data, reinforcing the interpretation that the event is a continuation of transform-related deformation, rather than a classic subduction megathrust slip that would produce large vertical displacement. But what happens when a titan in the north gives the ground a violent shove? Can that shove wake a sleeping giant hundreds or even thousands of kilometers away? When Alaska's crust breaks with the force of a magnitude 7 or greater event, the seismic waves it throws off do not stop at political borders. They race across ocean basins and mountain ranges. Do those ripples, or the small rearrangement of forces left behind, ever set off a separate megathrust rupture far away in Cascadia off the Pacific Northwest, or along the Aleutian Trench to the west? The evidence, when read carefully, delivers a cautious but consistent verdict. Large Alaskan earthquakes reliably produce seismic reactions at distant sites, often very small ones, sometimes worrying local aftershocks, but the scientific record contains no clear documented instance of a single Alaskan rupture directly causing an independent megathrust failure in Cascadia or in a remote segment of the Aleutian Trench. Instead, the picture is layered and nuanced. Stress moves through the crust in different ways, and whether that movement triggers a distant rupture depends on the target's pre-existing readiness and the character of the push it receives. To understand why remote triggering is possible yet rare for whole-scale megathrust failure, two physical processes must be distinguished: static stress change and dynamic stress stimulation. Static stress change is the permanent reconfiguration of forces after a fault slips. It is like rearranging the stacks of books that hold up a shelf. Nearby supports feel the new loading, but the effect fades with distance. Dynamic stress stimulation is the passing of seismic waves, a brief oscillatory shaking that can stretch or squeeze faults and the fluids within them. Dynamic stresses travel much farther than static stresses and can act thousands of kilometers away, but they act only briefly, like a gust of wind. Both mechanisms can nudge a fault already teetering on the brink into motion, but neither guarantees a massive megathrust will suddenly release. Historical cases illuminate how these mechanisms work in practice. Consider the large Denali fault earthquake on November 3, 2002, which measured roughly magnitude 7.9. The Denali rupture broadcast strong surface waves across the continent. Researchers documented triggered responses in geothermal and volcanic regions far to the south and west. Mount Rainier, parts of the Long Valley area, and other volcanic and geothermal sites registered small bursts of seismicity and tremor as the waves passed. These disturbances were generally small in size, but abundant and geographically widespread, recorded out to distances on the order of 3,600 kilometers, about 2,240 miles. Those observations show that dynamic waves from a powerful Alaskan earthquake can stimulate seismicity far away, especially in systems already near failure or in regions rich in pressurized fluids. But those stimulated responses were little more than annoyed whispers compared with the kind of continent-scale megathrust rupture that tears a long section of a subduction interface. If Cascadia, the long plate interface that runs from northern California into southern British Columbia and that last ruptured in a great earthquake in the pre-instrumental era, were to be triggered by an Alaskan event, the most plausible mechanism would be dynamic stimulation of a portion already critically loaded. But instrumental and historical records do not show an Alaskan earthquake causing a Cascadia megathrust rupture. Analyses of the Denali event sought explicitly for such an effect and instead found small, localized responses. Increases in microseismicity, transient tremor, and some triggered landslides and seiches. In plain terms, the Denali waves irritated the broad continental margin in places that were sensitive, but they did not make the entire Cascadia interface unstick. The geological reasoning is straightforward. A full megathrust rupture requires a favourable pre-existing stress state spread across a vast area and a sustained redistribution of shear stresses. A single passing wave, even a very strong one, more often provides a transient jolt rather than the sustained loading pattern a megathrust needs. The 1964 Great Alaska Earthquake, the mammoth magnitude 9.2 event that reshaped Prince William Sound and sent tsunamis across the Pacific, provides a further instructive perspective. That rupture dramatically rearranged the stress field across a wide region and produced many aftershocks and distant crustal responses from remote landslides to long-period oscillations in lakes. Yet it did not, in its immediate aftermath, precipitate a Cascadia-scale megathrust failure. The absence of such a triggered megathrust in the wake of the 1964 event underscores the general lesson. Enormous energy release in Alaska can rearrange stresses and cause remote reactions, but it does not often produce the specific stress configuration needed to topple a distant, locked subduction interface. Closer to home, within the Aleutian Alaska subduction system, there are clearer cases of a primary rupture spawning a large nearby companion. The sequence in 2020 in the Shumagin region of the Aleutians is illustrative. A magnitude 7.8 megathrust event occurred in July of 2020, and months later a magnitude 7.6 shock followed in the same general region. Careful studies interpret the second event as a very large aftershock or a closely related triggered rupture within the same subduction complex, rather than as a truly independent remote event. This is a critical distinction. When faults lie on the same plate boundary and are separated by only tens to a few hundreds of kilometres. A primary rupture can alter static stresses sufficiently to prompt another large slip nearby. That local triggering is a frequent behaviour in segmented megathrusts. By contrast, an Alaskan quake prompting an independent rupture in Cascadia, which lies more than 1,000 kilometres distant, would require quite different and less common conditions. Why do these differences arise? Static stress transfer dominates within a few fault lengths of the initial rupture, which is why aftershocks cluster around the main shock, and why neighbouring segments of the same system are the most likely recipients of altered loading. Dynamic triggering, carried in the body and surface waves, can act at much larger distances but typically influences only particular kinds of targets. Zones saturated with fluids, volcanic or geothermal systems, and faults already close to failure. If the incoming waves produce transient stresses aligned in a favourable way, they can open fluid pathways, reduce friction, or otherwise change the conditions on a fault enough to precipitate tremor or a small earthquake. The global scientific literature documents many examples of tremor initiation and clustered microseismicity in response to the surface waves of big earthquakes. Still, the amplitude and direction of those transient stresses often fall short of the sustained shear stress required to rupture a long, locked megathrust. This does not mean cross-regional triggering can be ruled out categorically. The science is probabilistic and constantly evolving. There are global examples where large earthquakes appear to have nudged activity in distant subduction systems, usually visible as increased rates of small earthquakes or tremor rather than as clearly induced megathrust ruptures. Modern seismic networks, GPS arrays and waveform catalogues give scientists unprecedented sensitivity to detect these weak signals and to separate chance clustering from physical causation. Each new large quake serves as a natural experiment, allowing researchers to model dynamic and static effects more precisely and to refine estimates of how stress perturbations change the likelihood of rupture on neighbouring faults. Applying these lessons to the Hubbard Glacier earthquake in December 2025 yields a pragmatic inference. That shallow strike-slip-dominated rupture produced its own aftershock sequence and broadcast waves across the North Pacific margin. Based on past observations from events such as the Denali rupture, the 2020 Shumagin sequence, and the 1964 megathrust, the most likely outcome is that the Hubbard event will produce remote, transient seismic responses, tremor or small earthquakes in susceptible locales, rather than initiating a Cascadia megathrust rupture or a distant Aleutian trench rupture on its own. If it alters probabilities on adjacent segments of the same transform or nearby subduction systems, the effect would most likely be modest and localized, expressed as a slight increase in short-term likelihood rather than an immediate large rupture. The questions we posed at the start, what broke, why did it happen, where it did, and might this be an echo of past doublets, find partial answers in the event's mechanics. A shallow strike-slip rupture on a connector strand of the Fairweather system influenced by the presence of the Yakutat Microplate explains much of the observed shaking and aftershock pattern. The region's penchant for doublets and clustered large events is historical truth, and while this quake is smaller than the great magnitude 8-class shocks of 1899, it reminds us that the same tectonic forces remain active. Over the coming months, careful analysis will fill in the full story, mapping the rupture surface, quantifying the slip, and refining our sense of how this event shifted stress across neighbouring faults. For now, the Earth has spoken again along that restless margin, and the scientific work of listening, translating and learning has only just begun. If you enjoyed this breakdown, don't forget to hit like, share it with fellow science enthusiasts, and smash that subscribe button. And tap that hype icon so this video can reach an even wider audience. Your support helps these deep dive investigations keep coming.